Now we're going to talk about a brand new topic, which is vectors. For our purposes, a vector is just going to be some quantity that has both magnitude and direction. So it has magnitude is the size and a direction. There's a more abstract kind of definition of vectors given at the start of the notes, because a vector in mathematics is a bit more of an abstract concept, where it says it's just an element of a vector space, and that these elements of the vector space, the vectors, can be multiplied by numbers called scalars to give another element in the vector space, another vector, or they can be added together, and this adding and multiplying has to follow certain rules. The vectors we look at are these Euclidean vectors. So they're the ones that we use to represent things like forces, where they can be added together. Like any two forces you add together gives you another force, and the two force vectors add together to give a third force vector. Things like velocity will be represented by vectors like this. So before we look at vectors, first we look at scalars. So a scalar quantity is a quantity that's defined in terms of magnitude only. So it's something that's represented by a number. So examples here are temperature in degrees, speed in meters per second, or time in seconds. So those are physical quantities that are represented by just a number, or a scalar quantity. Then by contrast, a vector quantity is something that has magnitude and direction. The examples given here are a force of 12 kilonewtons acting vertically downwards, or a velocity of 15 meters per second due west. So 15 meters per second due west is a velocity, a vector quantity. But a speed of just 15 meters per second with no direction is a scalar quantity. We represent a vector with a line segment if we want to draw it out, and the length of that line segment represents the magnitude of the vector, and the orientation represents the direction. So if this was point O and this was point A, then the vector that joins them, we would donate OA. And you see that little arrow over it is what lets us know that it's a vector that we're talking about. If this vector had a name, like just A, you'd write it with that little bar on top. We use that bar, or the bar underneath, to denote that a quantity is a vector when we write it down, rather than just a scalar. In print, a vector is often denoted with bold text, like this A here. Whereas when you write it down yourself, in handwriting, it will always be a little bar over or under the letter. A vector is a thing with magnitude and direction. It doesn't have a particular starting point. So if I draw another vector over here with the same magnitude and direction as A, and I call it B, it's not joining up the same 2 points, point O and point A, but it has the same magnitude and direction as A. The rule is given here for vector equality. Two vectors are equal if their direction and magnitude are the same. So it doesn't matter what the starting or ending points of the vector is. If I have two vectors A and B and they have the same magnitude and the same direction, then I say that the vector A is equal to the vector B. They're equal because they have the same magnitude and the same direction. Now, I said we could multiply a vector by a scalar, so here's how we do that. Our scalar that we'll use, we're going to call lambda. So you might not have seen that letter before, it's the Greek letter lambda, and it's going to be our scalar, so that's just a number. And let's say we have a vector B, and we multiply it by lambda to get a new vector A. What is that A vector going to be? We're given two cases here. If lambda is bigger than 0, then A is going to be in the same direction as B with magnitude lambda times the magnitude of B. So let's draw that. Let's say first of all that lambda is equal to 2, for example. Then we would say that A is equal to twice B, 2 times B. So let's say B looks like this. A then would be a vector with the same direction but twice the magnitude, roughly like this. Same direction, double the magnitude. Let's say, for example, that lambda was equal to minus 2. Well, then we're told that A is a vector in the opposite direction with magnitude lambda times the magnitude of B. So let's draw B here, like that. A will have twice the length in the opposite direction. So A will look like this. Notice I haven't given them the same starting point because that doesn't really matter. It's the magnitude and the direction that makes the vector. What if lambda was equal to 0.5? Well then, if B was this vector, A would be a vector with the same direction but only half the length. Or in this case, A is equal to 0.5 times B. So that's how you multiply a vector by a scalar. I also said that vectors are things that can be added together to give a new vector. And here's how you add them together. Let's say I want to add A and B, two vectors. I draw out my vector A and my vector B. Let's say these are the two I want to add together. What I do is I put the two vectors nose to tail like this. Then the sum of the two vectors is defined as the vector that joins the beginning all the way directly to the end. A plus B. It doesn't matter which way around I do this. I can put B first and then A. And my B plus A vector will be equal to the A plus B vector that we just did on the left. So A plus B is equal to B plus A. And when you draw it out to add them up, you can do it in any order you like. The other method for adding them up by drawing them out is the parallelogram method. And that's where you place them tail to tail. So if I draw A here like this, then I would draw B tail to tail with A like this. And to add them up, you complete the parallelogram like this. And the answer for your sum is the diagonal here. That's A plus B, your sum. So that's the parallelogram method for adding two vectors. They'll give you the same answer as the triangle method. What about subtraction? What if I say A minus B? Well, that's easy enough to do with what we have already. If I call it A plus minus B, where minus B there is just minus 1 times B, so it's a vector with the same magnitude as B, but going in the exact opposite direction. So if we pick two vectors, let's say A looks like this, and let's say B looks like this, we'll add them up first with the triangle rule. But first I'm going to need to know what minus B looks like. And in fact, it's just the exact same magnitude and the exact opposite direction. Minus B here in blue. So if I want A minus B, I'll use my triangle method on the A vector and the minus B vector. So I'll draw out my A vector again. I've drawn it a bit bigger here, but you get what I mean. And let's put in my blue minus B vector. And this vector here that joins the ends is going to be the vector A. As we've written it here, it's A plus minus B. But that's the same thing as A minus B. So that's how you'd subtract one vector from another. Now, what if I want to add together more than two vectors? Well, you can extend that triangle rule and just join the start of each vector to the end of the last one. So if I have, let's say A, B, C, and D. Let's say that's them. I want to add them all together. I just join them all up. And that red vector there is the sum of the four vectors A, B, C, and D. Crudely drawn, but you get the point, I hope. The algebra laws for adding vectors are about what you'd expect. So we have the commutative law that says for any vectors a and b, a plus b is equal to b plus a. We already saw that one on the last slide. There's the associative law. Well, that says that if you have a plus b plus c, you can put the brackets wherever you like. You can add a and b first and then add c afterwards, or you can add b and c first and then add a afterwards. It doesn't matter which order you do it in. Then there's the distributive law, which tells us how addition interacts with multiplication by a vector. So if I have the sum a plus b, and then I multiply that sum by the scalar k, it's the same thing as multiplying k individually in front of a and b, and then adding up the whole thing at the end. So k times a plus b is equal to k times a plus k times b. So that's the rules for adding together vectors and for multiplying them by scalars. In the next video, we're going to start breaking down vectors into their components in terms of unit vectors. And then we can start doing all our addition and vector calculations in terms of algebra instead of by drawing everything out and doing it geometrically. But for now, that's that.